In this video, I'm going to run through homework number 6 for our physics class. I'm doing this to supplement our discussions this week. I don't want you to use this video to complete your work and turn it in as your own, but after you've made your attempts, you can check your work against my procedures here in the event that we don't get to talk about these questions in class. Now the due date, of course, is wrong. This is from an older assignment, and the point values are a little bit different too. We're just going to do a 10-point scale on this homework assignment as well. All right, so let's jump right into it. Some of these questions come from older chapters, so I think that's a good reason why we should review all of these in one shot. So here we go. We have a wooden crate that has a mass of 120 kilograms. We have it resting on a wood floor with the coefficients of friction provided to us here. So that's mu s and mu k. Question A, what is the maximum force you can exert horizontally on the crate without moving it? So that's going to be our static friction force pushing back against us. And if you continue to exert this force once you break free, what's the magnitude of the acceleration? Okay, so very good. So in question number 1, we have mu s given to us, mu k, no units on either of those, they're just ratios, and then our mass 120 kilograms. In part A, I would argue that our job is to find the force of static friction, or what's the maximum amount of force due to static friction, and that is equal to mu s times our normal force. I believe the document said we're resting on a floor. I think it's implied that we're resting on a flat floor. That's going to be helpful because when we're dealing with a flat surface, we know that an object resting on it is being pulled downward due to the gravitational force here on Earth, and we have the floor pushing back onto the box. That's our normal force, and it's going to be perpendicular to the surface. So as long as that surface is flat, then our normal force that we experience is equal to the mass of the object times gravity. So with our given information and the formulas that we can use to answer the question, I might take this just a step further and put it all together. Since we're looking for the static frictional force, the maximum static friction force, and that's mu s times our normal force, I'll just go ahead and report this as mu s times mass times gravity. Now I have a formula set up and ready to go. No more isolating necessary to solve for our static frictional force. Now we can just show our work. And since there really wasn't any additional computations necessary, it may not be critical to perform a dimensional analysis, but I still do like the idea of going through that and checking to make sure that our units match. So we'll go ahead and do that when we're finished here. With mu s being 0.5, our mass being 120, and Earth's gravitational acceleration being 9.81, we would find the product of those three values. And off screen, I calculated that to be 588.6. And when we consult our significant figures, we're going to use two in this case. The sig figs associated with mu here. Well, I'm going to go ahead and assume that we've got at least two. I know that may not be shown in these two examples here, but if we needed more accuracy, we could go find a chart that provides us more accuracy. So much like our dimensions, unit conversions, I told students in class that we can use as many sig figs as necessary with unit conversions. We can also do the same with our mu values. So all of that to say we should report with two significant figures, and I like 590. Now we are looking for a force here, so I'd like to think that our result produces a Newton as a unit of measure, but let's just double check. The coefficient of static friction has no unit associated with it since it's a ratio, and our mass has a unit of kilograms, and our acceleration has a unit of meters per second squared. So if I have no unit times kilograms times meters per second squared, I do end up with kilogram meters per second squared. And as you recall from our definitions, the kilogram meter per second squared is the definition of the Newton force unit. So that works out very well. If we were able to get this box to break free and we continue to push with a force of 590 newtons, assuming that's our net force, then our net force is equal to the object's mass times its acceleration. Therefore, the acceleration that we're looking for, how much the box would accelerate by once we break it free, is the net force divided by the object's mass. So the acceleration, we'll go ahead and use the 0.5 times 120 times 9.81. I like going back to the original setup. I know that I could have typed in or written in 590, but I go back to the original. That way I can capture all the decimals before I round. So there's our net force and the object's mass. And actually, I've got to back up here. I got to think about this a little bit more carefully. We're pushing with 590 newtons of force, but we're still trying to overcome the static friction the kinetic friction forces that are present as well. So I should probably note that the net force is really the force of the push minus the force due to kinetic friction, and that's equal to our mass times acceleration. So here's where our net forces come from. Then acceleration is the force of the push minus the force due to kinetic friction divided by mass. So now when we start substituting values in, the force of the push ended up being the 590, or the 0.5 times 120 times 9.81. So there's the force of our push minus the kinetic friction force, and the kinetic friction force is our mu for kinetic friction, 0.3 times our normal force, 120 times 9.81, and all of that divided by our object's mass, 120. And with the calculator, I was able to obtain a solution there, 1.962. So our acceleration is 1.962. And here again, we hope that that's going to be meters per second squared, but we should double check with our dimensional analysis. By just setting some things up, we start to see some nice things happen here. We have no unit times kilogram meter per second squared, subtracting a no unit times kilogram meter per second squared. So that's convenient that those two are the same. We can subtract them from one another. You'll notice that I'm not going to bother turning that into or rewriting it as a Newton, because the difference of a kilogram meter per second squared, while that's a Newton, will be divided by the unit of a kilogram, and those units will effectively cancel, and we are left with a meter per second squared unit, which is precisely what we were after, considering we were looking for an acceleration. Now here again, we have two significant figures, so we'll call this 2.0 meters per second squared as our final answer. For the math-minded folks, you might have noticed that if we had expanded this formula, the force of the push minus the force due to kinetic friction divided by mass, the mass units end up canceling here. So this mass and this one being like terms to those two terms above will factor out of this mass down below, and g being a common factor comes into play here. We could have simplified this equation into this prior to even performing the computations with our calculator over here. And if we had noticed that ahead of time, that might give us a nice description as to what's really happening here when we compute the acceleration that results. But also it shows that the calculation could have been much more simple when entering into the calculator to obtain the same final result. So I thought I'd just share that with you while you're working on these. You might be looking for the mathematical approach to help you complete some of this work. Now, number two is kind of an interesting question. We have a board that's sandwiched in between two other boards that are held with this vise of sorts, this clamp. And the weight of the board in the middle is 95.5 newtons, and the coefficient of static friction is 0.665 between this board, and it's also the same between this one and the center board as well. So we have 2 points of contact, so we have 2 static friction forces at play here. What's the magnitude of the compression force? How much inward pushing force is necessary in order to keep the board from slipping? So hopefully that makes a little bit of sense. If the clamp is loosely holding the boards, and maybe it's mechanically fastened to these outer boards here. If the clamp is loosely tightened, then this board in the center could slide down. If we tighten it enough, then certainly that center board won't slide. And that's really what we're focusing on in this particular question. So the information that we're given is that the weight, I'm going to call that the force due to weight, of the middle board is 95.5 newtons. And we know that mu(s) is equal to 0.665 between the boards. Now, it might be helpful to sketch a free body diagram in this case. We've started talking about those last week. A free body diagram kind of gives us a tool to illustrate or indicate all of the forces that are at play here. So here's that center board that we're focusing on. I'm going to note that from that board there's a downward force. That's the force due to weight. Here on Earth we have this gravitational force trying to draw that board down. The compression forces, now you might be tempted to draw it this way. You know, we have this right side of the clamp pushing in on the board and the left side of the clamp pushing in on the board. And that makes sense from a visual perspective, but when we draw free body diagrams, we tend to move these vectors so that they're pointing away from the center point. So I'm effectively going to move this arrow to the left side, and then I'm going to move this arrow to the right. So we end up having the same vectors just emanating from a different position, and that's totally fine. Now, I may not be drawing these to scale. I may not have the dimensions correct, but you know, as far as the angles go, I know that they're perfectly fine. I don't know if the lengths of these are correct. But I'm going to call these arrows the normal forces. Now, I know it's coming from the compression or the squeezing of the boards here. But remember, we have the surface that's occurring right now. And while this clamp is pulling in on the board is also pushing back on the wood. And so when that pushback, or when that compression in is formed at a 90-degree angle, we'll go ahead and call that a normal force. So it's normal to the surface. We've got 2 of those, one from the left side and one from the right. And then finally, the force that's preventing this thing from falling is that slipping force, that frictional force that's in between. And each of these points of contact produce a frictional force. So we have Fs on the left side and Fs on the right side. So we have 2 frictional forces emanating from that body. Now that works well. I think that's a fine free body diagram. But personally, I prefer to do this instead of 2 of these forces side by side, since those 2 are acting together and compounding with one another. I'm just going to draw them stacked on top of each other. Now this gives me a nice visual representation. If this board is not sliding vertically at all, if it's not sliding down whatsoever, then the length of this upward vector, or combination of vectors, needs to be the same as the length of this downward facing vector. Those 2 would indicate a net of 0. And then similarly, the normal force on the left side and the normal force on the right side should be the same length as each other as well. And so the sketch does pretty much represent that. So now I feel confident in setting up my equation. And so I would say the formula looks like this. Since we're worried about the boards sliding, I'm going to pay close attention to the vertical vectors here. I have 2 of these frictional force vectors, and they're static friction force vectors, that must be equal to the magnitude of the weight vector. Now, I don't really know what the frictional force is just yet, but I do know that frictional force, static frictional force, is equal to mu s times the perpendicular forces, or the normal forces. And as the instructions indicated, that's exactly what we're looking for, is this perpendicular or normal force. So I would state that the perpendicular force, the normal force, is equal to uh, the weight force divided by 2 times mu s. Now I just realized partially through this problem that I labeled normal force F sub n, and then at some point I switched to F perpendicular. I think either of those notations are acceptable, but since I started with F sub n, I'm going to switch back to that as well. Sometimes you'll see n as a vector representing our normal force as well, so just be on the lookout. I think the formula here looks pretty good. Now we can start showing our work with our formula. We know the normal force is going to be equal to our weight force, 95.5, divided by 2 times mu s, and mu s was given to us to be 0.665. Now, real quick on our unit checks, 95.5 is a Newton, but then we've got a scalar 2 multiplying by another scalar, a mu value, which has no unit. And that's pretty good, because when I divide these two numbers, I was hoping to get another Newton as a result, and that's precisely what we're going to get. And so the calculator shows 71.8045. 71.8045 newtons. And since we should be reporting using significant figures, in both cases we were given 3 sig figs, so I like the answer 71.8 newtons. So each frictional force, which is generating our normal force for us here, indicates that each side of the clamp is exerting 71.8 newtons of force. All right, so those first two questions were similar to each other and from a prior unit. Before I start the next few questions, I think I'll stop the video here so that it doesn't get too long, and you can pick and choose which ones you focus on. So if you need help on any of the remaining questions, please check out those other videos. Thanks.